to the same answer.
No problem. Okay, so two main questions. First, two different methods converge to the same answer given the same force field. And the second one is how quickly the calculation converge. So I'll give first an introduction of the challenge and what it consists. I'll dig into a little deeper into how we run the reference calculations, as this is important because, well, I'm going to spoil the punchline, but the results do not converge to each other. And so we want to have every critical pair of eyes that we can have to see if we have actually methodological issues here. And then I'm going to have a quick overview of the results. So first of all, how do we measure the cost of a method? That is not a trivial task. It is an important measure. I mean, computational cost for methods definitely enter the decision-making process, both in industry and academia. We all know that CPU, GPU time is not a very fair metrical comparison because it's dominated by hardware. And even if we run different methods on the same hardware, different software package can make the difference, and implementational details actually affect the final times. And ideally, we want to decouple the cost of a method from the cost of its implementation. Nanoseconds, microseconds of MD are traditionally listed in the literature, but they're not a very good measure of the cost. It depends on the time step, and they lose meaning when as soon as you introduce some Monte Carlo pose. A third measure that we proposed was the number of energy evaluations. This is not ideal either. So first of all, it cuts out everything else that is not energy evaluation, but that's usually acceptable because in this kind of statistical methods, that's the most expensive part of the calculation. So it's a good approximation. The main problem is that it really depends on the system size. So two energy calculations are not the same. In many of these methodologies, we actually have two phases, a complex phase and a solvent phase, and they have two very different sizes. So as depending on how much effort you spend on one phase rather than another, the cost is not going to be fair. And also, systems of the same size, the calculations that the method requirement are not always the same. So energies can be updated sometimes. When you switch the Hamiltonian, only the terms that change need to be updated. When you do a Monte Carlo on a subset of move, you don't need to compute all the n-squared interaction plus bond plus everything. So we decided to ask for the participant both CPU and GPU time and number of energy evaluations. We based our preliminary analysis so far on the number of energy evaluations as the main metrics because it solves many practical problems. But the main message is that this is just an approximation, and there is not a perfectly good solution. Our software package are not don't make it very easy to measure exactly what is the number of terms that you use and assign a cost to different functional forms. So we extrapolated two hosts and 3 ligands from the main host gas challenge, the original octa-acid and the cucurbiturials. The reasoning was to mix fragment-like guests to more bulky and drug-like guests. We also picked 2 of the octa-acid guests because we were hoping to have relative free energy calculation submissions. Unfortunately, we didn't have. We generated 5 different replicas for each host guest system. These are docked poses that I generated using OpenEye. The 5 replicates starting configurations for the octa-acids are relatively similar, but that's a fairly simple guest. There is more diversity in the cucurbiturial guest, and more importantly, we have one flipped binding mode that I was talking about during the first talk. we try to come up with a common setup because there are, of course, issues between different software packages. Not all packages are compatible with the same method. So we decided to go with AM1 VCC charges, GAF T3P box, and neutralizing and buffer chlorine and sodium ions. And the files were converted in many different formats. Thank you to Michael Schurz and Travis Jensen. One important point is that traditionally, the long-range treatment is technically part of the model, but they are never encoded into the input files and in the force field. Traditionally, these have been considered like a gray area between the method and the model, and the different software packages actually have different implementation. They support different options. So we can only suggest the long-range treatment. We run calculations using PME with a cutoff at electrostatics and van der Waals of 10 angstrom. And a switching function for the van der Waals. At the end, we asked to the participant to submit free energy estimates at regular intervals of the free energies, 1 to up to 100%. Submit the total cost and energy evaluations and the total time. And with the requirement that replicates that belong to the same system, so all the 5 replicates for the cucurbitural gas, for example, need to have the same total cost in a number of energy evaluations. And this is because the idea was to be able to match different replicas at the same times to be able to compute confidence interval on the estimates of the method. So we performed the reference calculations using Yank. This was a software that was initially created by John. It went through many hands, and now the main developer is Levi Naden, and I'm actually the developer as well. We use a lot of different packages underneath. It includes Yank also includes an automatic setup pipeline for free energy calculations that we use to set up the sampling systems, and it's based on all these wonderful libraries. So first of all, the thermodynamic cycle that we used, there are a couple of important things. We annihilate electrostatics and decouple van der Waals interaction. The steps with not the full arrow here are only reweighting steps. So we don't actually sample from these two end states. We just reweight the harmonic, the bound state using an harmonic restraints that we use throughout the simulation to a state that uses square well. And this is a step that we took to remove the bias that we introduced by adding the contribution of the harmonic restraint. And the second thing to keep in mind is that this ligand is charged in the simulation for all 3 systems, and we remove a counter ion. We discharge the counter ion and we decouple the counter ion, and here we recreate it in solvent to keep the final charge equivalent and the net charge to 0 and avoid artifacts for the PME. So this is the effect of the reweighting from the harmonic to the square well. The harmonic restraint introduces a bias that seems to be non-negligible. The spring constant for the restraint was actually fairly low, 0.17 kilocal per mole per squared angstrom. The other 2 replicas are similar, and the profiles are very similar for all of the 3 systems. The orange line is before the reweighting, so the end state in this case are the ones with the harmonic restraint on. And after removing the harmonic restraint and basically reweighting to a state that has a square well restraint, this is the final free energy. This is still it's nice to see a plateau. This is what we expect here, but the choice of a cutoff is still an arbitrary choice. So we try to make it as less arbitrary as possible. The good news is that it doesn't matter that much, but we adopted this strategy. We are basically selecting the 99.99 percentile of the restraint distance in the bound state. So the idea is we want the simulation defined if it's a well-behaved simulation, like in this case, where the gas doesn't leave the binding pocket and remains there. we let the simulation define what is the binding site, and we try to get all the samples from here. And from here on, we can cut before we actually run out of samples right here, because after here, the weighting to the square well is the overlap between the states is gonna be so low that the statistical estimate is not gonna make sense anymore. So a couple of things to notice here is that it's good to see that the harmonic restraints is soft enough to not actually cut important configurations. So the full decoupled state here, the distribution has a much wider support, which is a good news. Here the bound states is relatively is more peaky. And the second thing that I thought was curious is after discharging the guest, the orange distribution here is for sterics only. The guest actually crawls into the basket a little more, which is expected. The restraint has been applied between the center of mass of the two molecules. So the center of mass of the octa acid here is towards the bottom of the basket, and so it's always nice to see something that makes sense. To accelerate the propagation, we use Hamiltonian replica dynamics, and we mix molecular dynamics and Monte Carlo moves. So this is our typical protocol. We perform a Monte Carlo translation of the guest, a rigid translation, a rigid Monte Carlo rotation of the guest. We perform 500 steps, 2 femtosecond steps, so 1 picoseconds of Langevin dynamics and Monte Carlo barostat. Well, sorry, this is a little bit misleading. The Monte Carlo barostat step is done every 50 femtoseconds of Langevin dynamics. And at each iteration, we perform an Hamiltonian replica exchange through about 1 million global Gibbs swaps. Okay, the good news is that the reference calculation seems to have converged to the same value. We hope this is the right value, but this is already good news. So this is the mean free energy across these different replicates with 95% t-based confidence interval. And the number of energy calculations here include also the calculations that we need to perform to compute the full energy matrix that we feed to MBAR and that we use to run Gibbs sampling very fast. These are the other two calculations for the two octa acids, and we get very good convergence in this case too. The confidence interval are 0.02 kilocalorie per mole, 0.05. The CB8, the guest of CB8 was a little bit bulkier, and we had more problems converging this. It also required a larger number of alchemical states. So Travis Jensen and Michael Schertz are providing a second pair of reference calculations to confirm our own value. And this is when the first problem starts to pop up. So we still have differences between the two. It might take a little bit more for this second pair of reference calculations to converge. I was talking to Travis before. We have already sorted out a few issues, but the goal is to have these two free energy calculations to resolve the discrepancies, because we can't really compare other calculations to us unless we have some confidence in our final values. So there have been in total 2 submissions to this challenge, so I can literally show you all the results. And many thanks to both of the participants actually. So this is the calculations that went better in terms of bias. I'll explain the many different lines. So the orange one is the reference free calculations that we run. The 5 light trajectory here are the 5 replicates, and the blue, dark blue here is the mean of the 5 trajectory of the submission. The blue shaded area is the 95% TBS confidence interval. So Mikhail already showed you this. They had few replicas with these weird spikes that I would be curious to talk to them and figure out what these were for. I think they eliminated from their. They mentioned they had problems, so probably this is just some technical issue. But a good news is that the Hamiltonian replica exchange seems to make the difference in terms of convergence between different replicates. This method does not use replica exchange. I think it's just parallel replicas that run independently. One main difference is that according to the meta section, they didn't use PME. They used reaction field with a 12 angstrom cutoff. That can make a big difference in terms of the final free energy. I'm actually surprised that this agrees that well. This green line here is the final value that we reached with the Hamiltonian replica exchange calculations. I had to truncate here to match the number of energy evaluations here. And this is for CB8G3. This is for the 2 octa acids. And these are supposed to be relatively simpler from a sampling perspective. The gas is smaller, so there are not many atoms that you need to decouple from the system. And both of the methods converge. Actually, the Y scale here is the same, but both methods converge, but they converge to different values. And this is the second submission. So this method is not alchemical. Try to estimate the free energy by estimating rates of binding. So next steps. So first of all, we need to get the reference calculations to agree. That's step number 1. We still have some leads beside the convergence. In the best case scenario, this is a methodological issue. It's fast to track down. In the worst case scenario, we may need to compare the conformations that we are actually sampling and see if there is actually a sampling problem here. And the second step, once we resolve this, in the ideal scenario, we would like to get in touch with the people that submitted results and to figure out why this difference arises. It could be that this is just caused by reaction field, different models, but that's eventually the goal of this challenge. So just a conclusion, overall, I think this was a successful challenge, even if it wasn't the kind of outcome that we were expecting it. The main question that I asked myself is, here we have taken out the model or the full force field out of the equation. We are just comparing methods, and the results between them are so different anyway. So how much do we have to actually have in common to make different methods to agree? That's a big question here, and especially considering that we are using host gas systems because we think they're relatively easy to sample over. But a big advantage of this kind of study where the input files are shared across all of them is that it might be actually easier to zero in the methodology because there is only so many things that can go wrong. You can't blame the force field anymore. And a second thing for future challenges of this is that we have only 2 submissions. This challenge was probably not as advertised as the other, but I think one of the main problems is that the barrier to enter the challenge is actually higher. Your package needs to support the specific models that we set up. In a way, this was actually a little unfair. I mean, I prepared the calculations and the setup for the protocols that I'm used to run, and different package and different groups are actually very confident with maybe other protocols. So how can we lower the barrier to enter more of this kind of study and try to actually make the methods converge? And this is probably one of the best ways that we have to figure out what methodological issues actually matter in free energy calculations. And I'll thank you, everybody that I thanked before again. And in this case, I also have the Michel Group and Alex Dixon that participated to the sampling challenge, and Travis Jensen and Michael Schurz that are helping with the second set of reference for energy calculations. Thank you.
Thank you, Andrea, for getting us started towards the steel tables of simulations. Let's thank our speakers. We've